So this next clip now is going to deal with compound systems, which are very useful if you want to combine things. And they're really a powerful concept in quantum mechanics. And the key idea behind combining things is that physical systems are constantly interacting with their environment, and many times you need to incorporate this influence in a larger system, or you have more than one system which you might need to take into consideration. And here we're going to show you how to describe compound systems within the vector space framework using tensor products. Also, how to construct density metrics for compound systems and what all these things entail. So just to pose the problem, let's consider two quantum systems A and B. So here you have system A on this table and B. With them, there are two state spaces associated. So this curly A here is associated with A, and this curly B here associated with B. They are described by these orthonormal bases. So this basis ket A1, H2, A, blah, blah, etc. span space A, and these cats B1, B2, etc. span the space B, and they have dimension dA and dimension dB. So we have these two quantum systems, electron 1, electron 2, or for instance, electronic and nuclear degrees of freedom in a molecule, etc., etc., etc. So what we would like to do is the following. We would like to combine A and B, but we need to be careful about how we're going to do this, because we need to ensure that whatever we do, the vector spaces behave the way they should. So their axioms should be satisfied. And we would like to have states in this compound Hilbert space that represent state Aj of system A and state Bj of system B. And also they have to satisfy the principle of superposition. And this compound state space that you create has to behave like a state space. So everything we have defined so far for state spaces must hold. And in order to satisfy, the tensor product is on the other page, but in order to satisfy these requirements, Hilbert spaces A and B, they are combined via a tensor product. Let me see, I can paint this. A pen. Okay, so I'll paint the tensor product. So it has to be A tensor product B. That's how they have to be combined. So we're going to see this in more detail, and I'm going to go more slowly than here because this is somehow new to a lot of people. So we're going to do some whiteboard type derivation starting from the next part of the lecture. So the key question that we would like to ask is how to construct a compound state space and its objects, mathematically speaking, operators, state vectors, etc., etc., etc. So let's have a look at what we are given. We have two sets of basis states in space state R, A, and B. So we have basis states AJ, whereby J goes from 1 to the dimensional GA in A, and we have the basis states BK, whereby K goes from 1 up to the dimensional GB in the subspace B. That's what we have. And what we would like to do, our task, is to identify a set of orthonormal basis vectors for the compound space A tensor product B. Note that so far we have assumed that these guys here are orthonormal. These guys are orthonormal when we are considering a discrete basis, but the same holds for a continuous basis too. So let's have a look. And how do we do it? These states are constructed by pairing together basis states from A and B. For instance, you can have this state, which is A given by the tensor product of A1, B1. And this means that here, this is describing system A in state A1, and this is describing system B in state B1, and this describes a state accounting for that in a tensor product B. Now, it's important to bear in mind that there are other conventions. For instance, sometimes you see in the literature that the tensor product is omitted, so you can write it like this. Note that here we emphasize the tensor product, but here it was omitted, or you can specify the same by putting a comma. And if you would like to write a full basis, remember, this was one arbitrary state that we just constructed so that you see how it goes. But if you would like to construct a full basis, and you have to span all the compound state space, then what you have to do basically is to include all pairings that you may have, and the number is going to be dimension of A multiplied by dimension of B. So A full basis can be constructed by including all GA times GB pairings, which means that if you would like to describe an arbitrary state psi in the compound state space, this is going to be given by this expression. So you have sum over J going from 1 to dA, which is dimension of A, sum over K, going from 1 as well to dimension dB of CJK, AJ tensor product BK, and these are coefficients which are specific to this vector you're constructing. So this is just that you remember arbitrary state vector in the compound state space. And as we defined in the first lectures, okay, this has to be a weighted sum. Here you also see this has to be a weighted sum. And if you are wondering where these things occur in practice, one may have, for instance, many particles. So you could say, for instance, that system A is one particle, system B is another particle. You could have several degrees of freedom. This is very common if you are dealing with molecular dynamics, because you are going to have electronic degrees of freedom, you're going to have vibrational degrees of freedom, rotational degrees of freedom, and you have to find ways of taking all these things into consideration. Also, you can combine angular momenta. Some of you may have seen this. So all these things are examples of physical compound systems, and the list is really non-exhaustive. This is a very, very powerful way of taking these things into consideration, mathematically speaking. And I'm going to give you a very simple example, which is convenient for us, because here the state space has just, when you try to combine, is going to be 4-dimensional only. And these are 2 spin-half particles. So first particle spin up and down, second particle spin up and down. So if you write the basic states, for the compound system, we're going to have 4. So first particle, particle A up, particle B up, particle A up, particle B down, particle A down, particle B up, and particle A down, particle B down. You see? So note dimension, we had dA here was 2, dB was 2, and now compound space we're going to have 4. And indeed, we have 4 basis states which are going to span this dimension. And if we write this in general, we're going to find that a general state psi can be given by, again, the weighted sum of these compound basis states. And this is giving you the weighting. These are coefficients. We have, again, a weighted sum. So we're spanning all these compound state space. And now we can ask the question, we need to define now scalar products, inner products. How are we going to do that? So let's have a look at scalar, or if you're more familiar, inner product. And we need to define this in a tensor product B. So how we're going to do it, we can use the scalar products in the subspaces A and B. So let's have a look. We're going to consider this cat CK in the compound state space, which is then written as AI BJ tensor product, whereby this is a cat in A, this is a cat in B. And we are going to define another one, CK dash, which is going to be AI dash tensor product BJ dash. And what we would like to calculate is the is the inner product of CK and CK dash. So this is CK, CK dash. This is what we don't know. Now, we assume here that CK AI and BJ, all of them, they form orthonormal bases. So when we calculate this, we're going to have then CK dash is going to be AI BJ AI dash tensor product BJ dash. This is going to give you AI dash BJ dash, And we said they are orthonormal, which means that you are going to have Kronecker delta I dash, Kronecker delta J dash. So that's pretty much all these rules. They have to continue being valid. And this, if you wish, is going to be KK dash. Now, how about eigenvalue equations? Well, in this case, let us consider an operator O, which is arbitrary. And this operator OA is going to act upon AI and is going to give you AI. So this is an eigenvalue equation. And one thing we can say from here is that OA or AI is an eigenvector of OA, of this operator OA, right? Now what we would like to solve is the following. We would like to solve or to compute OA CK. I mean, this OA is something that is acting upon this subspace A onto these vectors of the subspace A. And when you do that, you get OA, AI, tensor product BJ. This is going to act upon this guy. So you're going to have OA, AI, tensor product BJ, and you end up with AI, tensor product BJ, which is equal to AI CK, which means that OA also solves the eigenvalue equation in the compound system. Which means that CK is an eigenvector of OA with eigenvalue AI regardless of what PJ may be. So we are in a situation now in which we can say that this guy is also an eigenvector. And I'm going to give you some physical examples so that you see how this goes. For instance, let's consider the state space of a 3D particle. This is a nice example, and we're going to consider here, for simplicity, Cartesian coordinates, but note that here we're going to have continuous basis, and we're going to construct this space. So we're going to get EXYZ, which is our compound state, and this is going to be the tensor product of the one-dimensional state spaces EX, EY, and EZ. So this is the this is the 3D compound state space, and these are the 1D state spaces. But don't forget that they need continuous basis, because all these coordinates x, y, and z, they vary continuously. So we're not going to have sums, we're going to have integrals and all those things we have seen for continuous basis. So if we have basis in EX, this is going to be this X basis. In EY, is going to be the Y basis. And in EZ is going to be this spanning set. So that we can construct this ket R, which is X, Y, and Z, which is the tensor product of X, Y, and Z. Let me move this a bit here. Okay, this is a nice result. We're already applying what we've learned. So this is our compound state vector for the basis. And now we need to look at eigenvalue equations. So let's check. Let's first analyze what we have in X, Y, and Z. So let's consider the X, Y, and Z operators. And we know how they act upon these kets that are spanning X and Y and Z. So if we apply them to the ket X, we're going to get X. If you apply Y to the ket Y, you're going to get Y. If you apply Z to the ket Z, you're going to have Z. So basically, on the left-hand side, you have operators, right? X, Y, and Z applied to kets. And on the right-hand side, then you get the value of the coordinate X, Y, and Z. So we know we have eigenvalue equations. And what I'm going to argue is that R, which is X, Y, and Z, are simultaneous eigenvectors of the x, y, z operators. Here the emphasis is pretty much on simultaneous, and how we're going to verify this. What do we want to achieve? We want to achieve that xr is going to give you xr, yr is going to give you yr, and z applied to r is going to give you zr. I'm going to show you for x, but you can pretty much use the same train of thought. So if you write xr, you're going to have x applied to x, and then you're going to have y and z, and we know that this guy here is xx. Agree? Which means that this is going to give me xr, which proves the claim. Can do the same for y. So if you have this, you're going to have x. Now you know you act this on the subspace spanned by the y vectors. So you get y r, and you can show that the same is going to hold for z with the point that you apply then is onto z. So this does hold. And we need also to check orthogonality. We write same holds for z. Orthogonality or if you want to be more precise, orthonormality. Note as well, say what happens if you want to calculate this, if you want to calculate r naught. Well, this is going to be, from the definition that we have, r is going to be x, y, z, and r naught is going to be x, y, z. So we have to compute this bra. We have the bras, we have the cats, we have everything. So r in a product with r naught is going to be, here I forgot the naught, sorry. X naught, y naught, and z naught. Now note that x naught is going to be delta x minus x naught, y naught is going to be delta y minus y naught, and in a product of z with z naught is going to be delta z minus z naught. Basically what you're doing is you have a continuous basis, so instead of having Kronecker deltas you have Dirac deltas, okay? Dirac deltas instead of Kronecker deltas, because the basis is continuous. Fair enough. So we see then that r naught is going to be delta x minus x naught, delta y minus y naught, delta z minus z naught, and this is also delta R minus R naught. So this is one way of defining this basis, and actually you can see this is orthonormal. And we have done a bit quickly, okay, we discussed tensor product of an operator. We applied the operators here to look at the eigenvalues, but we have done a few things which may not have been clear to some. So we're going to have a look at tensor products of operators. So we're going to assume that we have the operator O acting in the subspace A, and we have the operator Q acting in the subspace B. Now, let's consider also that we have a ket psi in the compound state space A tensor product B. This is our assumption. What are we going to do? So that tensor product, we want to compute tensor product of O and Q applied to psi. This is what we would like. So let's do it. We have O tensor product Q applied to psi. This means that we're going to have sum J going from 1 to dA, and then K going from 1 to dB, CJK. Now we apply O to this guy, and we apply Q to this guy. Which is, if you have an operator and you know it's acting in a subspace A, it's only going to change gets from that subspace. And if you know you have an operator which is acting in the subspace B, it's also only going to change operators or state vectors in that subspace. And this is something you have to bear in mind if you want to do these things consistently. So the tensor product is going to act like this, and you find sometimes operator of this form, operators of the form O times identity, etc., etc. So they will act as the identity in all but one subspace. And they are written typically. For instance, if you want an example here, this guy. We wrote it quickly because you should know what you're doing, but this you could write as X identity, or you could even write here as well, identity Y identity. So It's just because we were doing this very quickly and you are expected to know at some point what you're doing. But one way, if you really want to distinguish, you can write it like this, are written as OA, which is O acting on A, identity, identity, blah, blah. Or for instance, OB, where you have identity, O acting on subspace B, etc., etc. So this subscript identifies the subspace in which the operator acts. Now, we need to consider also matrix representation because we use this a lot. So we need to understand how the tensor product is going to work in this case. So I'm going to go it quickly. And if you have then space A, and you know the dimension is GA, you have space B, dimension GB, you know that A is going to have dimension, a tensor product B is going to have dimension GA, GB, right? So this means that in the matrix representation of states, in AB will be represented by GAGB vectors, which means that these vectors is going to have, they're going to have 4 entries or more depending, GAGB entry, and operators in AB will be represented by GAGB tensor product GAGB matrices. Let's have a look. Again, spin half particle is quite useful because it's widely used and you just have 2 dimensions for each particle. So we have, for instance, that this state, which we have discussed at the beginning of the lecture, is isomorphic to this column vector. Note that this is a representation, this is not the state. So that's why I put this tilde here on top to say that this is isomorphic, that you're doing a mapping. I know a lot of people are struggling with that, but this is an important subtlety. So we construct the tensor product and we get a vector with 4 entries, 1, 0, 0, 0. We can do the same for one spin up, the other down. We're going to have 1 times 0, 1, 0 times 0, 1, which is going to give you 0, 1, 0, 0. And now you can verify. I'm not going to do this into detail, but you can verify somewhat similarly. Make this like this, okay? We have that A and B, one A down, sorry. This I have already done. That you have A down, B up is going to be 0, 0, 1, 0 in this representation, and spin down A, spin down B is going to be isomorphic to 0, 0, 0, 1. Check that. So please try this out so that you know how this holds. I'm not going to derive this because it's pretty much like the other ones. And for matrices, what we're going to have is, if you have a P1, P2 matrix, P acting in A, and if you have Q1, Q2 matrix, Q acting in B, what you're going to have is we will have a P1, Q1, P2, Q2 matrix in A tensor product B. So it's going to be something like this. P tensor product Q, P11, Q, P1, 2, Q, P1, P2, Q, P1, sorry, Q. And then you have P1, 1, Q, and you have P1, P2, Q. Here is P2, sorry. Okay, so it's going to be pretty much like this. And this lecture then I'm going to finish now. And what I'm going to see next, is we're going to discuss entanglement, which is useful in many areas of physics, especially if you're doing quantum information.